So, yes, Harry's here to talk to us about his augmented code editor for a functional programming language. So.
That's me. Cool. So, to start off, I'd like to ask you a really simple question, which is, why did you get into computing? I know why I did. I got into computing because of my grandfather. And my grandfather was a high school maths and physics teacher, and using his entire ST, he created a number of interactive graphical maths and physics simulations for students, like this one. Or like this one, which shows you Snell's law. You can click anywhere on the top of the screen, and it draws out the ray, which gets refracted as it reaches the border of the two media. You can click as many times as you like, and the ray changes instantly. You can change any of the parameters, and instantly see how changing the parameters changes the system. So when I was like 10 years old, this was mind-blowing stuff. Like, this opened whole new worlds of thinking for me. It really showed me that the computer is just the greatest tool for thinking, for learning, for creating. I mean, that's why I'm here now. So, fast forward like a decade, and I'm looking at this all day, every day. Some colorful text inside a black rectangle. And I switch to a different black rectangle, and I type in my magic incantation to set my computation in motion, and what I get back is just not what I expect at all. So I switch back to this rectangle, and I sort of have to run my program inside my head to figure out what went wrong. Kind of like this. So I'm staring at the code, and I'm sort of parsing it in my head. I'm sort of building a mental model inside my head, this sort of state machine. But that's a really fragile process. That, you know, it's in my head. Why am I running this program inside my head when I've got a computer right in front of me, which is supposed to run programs for me? I can't see what's going on because the computer isn't telling me. So obviously the programming world has developed a lot of really sophisticated tools to solve this. And these are surprisingly sophisticated. They tell you what's happening at a given point in time, what certain values are at a given point in time, but they never tell you why those values are what they are. Why is this value null? Why was this method called, not the other one? I've spent too much of my life rearranging log statements to figure out these sorts of mistakes. So obviously, we've developed some much bigger and better tools. IDEs, integrated development environments. These are super powerful. These really allow you to write tens of thousands of lines of code to like move data from one database to another, and they're super powerful. They do make a lot of people's lives a lot less miserable. But the problem with these is that they haven't changed the model of programming, the process of programming, in any significant way. You're still writing colorful text inside a rectangle, and the big innovation now is you press this button up here, and you wait a bit, and you see the output down here. And, that's the same thing we did 20 years ago before we had IDEs. And look, I'm still just logging. I think there's a better solution. I think we can do better than that. And, yeah. So in 2012, this guy named Bert Richter came along. And he showed the programming world just what you could do with today's computers. He showed us a number of demos. You might recognize this one from earlier, which show us that we can really go past editing text for writing programs. We have these amazing computers at our hands, and we should be able to just see what programs are doing interactively. So here, for example, these are all the future points in time that this character is going to move, and as he changes the value in the code, the character changes, the trace changes. Like, for anyone who's interested in programming, I definitely recommend you to watch this talk, because it just shows that we're not there yet. But the most important part of this talk isn't these demos. The most important contribution is this principle, which is creators need to have an immediate connection to what they create. And I hope that immediately you can see that that's totally violated by current tools. And, well, since then, like the past 3 years or so, a lot of people have tried to like build these sort of interactions into current systems, but these have mostly failed. And I think what they've shown is that mostly is that we kind of need to rethink programming systems at a slightly more fundamental level. So a few months after, Brett Victor wrote an essay called Learnable Programming, which is a kind of critique of some implementations of these demos which just completely miss the point. And in it, he gives us a really useful conceptual framework for thinking about programming systems. So a programming system is a programming environment and a programming language. A programming environment is on the computer. So that would be like the compiler, the editor, the runtime, the debugger, everything on a computer that lets us program on a computer. And the programming language is inside the programmer's head. It's what lets us think about what's happening inside the computer, much like any other language lets us think about what's happening in the real world. Right? So why is this useful? Because now we can look at these parts separately. So for example, the environment should allow me to do these things, according to his essay. Read the vocabulary, follow the flow, see the state, create by reacting, and create by abstracting. And I'd like you to keep these in mind as we see the programming environment that I've created. But let's look at the language now. According to Brett Victor, the language should provide identity and metaphor, decomposition, recomposition, and readability. And let me just focus on two things that current languages are particularly bad at. Decomposition and recomposition. How do I break down my thoughts into mind-sized pieces, and how do I glue these pieces back together again? So this is an example in processing, which is a sort of supposed to be like an easy introduction to Java with a nice graphical library on top. It sort of hides away all the object-oriented parts of Java, so what you're looking at is just pure imperative code, really. So here we have our nice flower stem. Here's the code for that. Here we have our petal. And we now want to compose these two. So we just take this code and we paste it in here. Well, what happens is that the leaves and the grass turn red. And why is that? Well, so in an imperative program, these lines get executed step by step. So we fill, and then we draw the thing, and then we fill, we draw the stuff here, and then we never fill back to green again. You might think, oh, whatever, that's not a big deal, you know? That's what we're here for, we'll just add that other line. Well, it is a big deal because we now can't reason about any of these lines of code independently. This block of code is the smallest unit that makes sense at all. I can't take out any parts of this code. None of these lines of code have any meaning on their own. They all depend on prior statements. And you know, that's why we need step-by-step debuggers. They show us what happened previously so we can figure out what the current state is. And that's the sort of next step improvement on logging. This is the Chrome debugger, which is an amazing tool, but like any serious IDE has these, because they're really essential to debug imperative programs. Why? Because variables can just change over time, and you can't really see why. So the point I want to make here is that our programming environments are fundamentally shaped by the underlying programming languages. So I wanted to come at it from a totally different perspective. My entire project is all about answering the question, what could an editing environment designed entirely for a pure functional programming language look like? Well, to answer that, we first need to understand what are the properties of a pure functional programming language. Well, first off, an example of a pure functional programming language that we all know at Imperial is Haskell, right? Has anyone here not used Haskell? Yeah, well, okay, so in Haskell, you can't reassign variables. You can't say x equals 5 and then assign something again to x. So how do you change anything? Well, you define values and then you apply functions to those. But once you've defined a value, it never changes. values are immutable. Another really important property of functional programming languages is that functions are pure. Given the same inputs, they will always give us the same outputs. Given the same inputs, they will always evaluate to the same thing. And put together, these two properties enable the style of reasoning, equational reasoning, which is really similar to mathematical equations, which you can't do at all in the paired program. On a value level, all of these are equivalent. You know, I can replace these anywhere I see them. So another really important property of functional programming languages is that functions are values just like any other, which means that I can pass them as arguments to other functions. So one of the most widely used, this is called higher order functions, one of the most widely used is map, which takes a function and a list and then applies that function to every single element in the list. And so what this shows is how this actually gets evaluated. So as you can see, there's no concept of lines of code. It's all these expressions, these bubbles, which get evaluated. Each of them has a specific value, and the value is sort of popped in this case until we get our final value. Another really important higher order function is, or class of higher order functions is fold, which takes a list, an initial value, and a function which sort of reduces or folds this list into a single value. One thing to note here, again, is that it doesn't really matter which of these bubbles I pop. And in fact, different functional languages have different approaches to which bubbles to pop at what point. It doesn't matter. Right, so now I've given you all these nice properties, which I hope you agree are pretty nice. So now I need to find a language which actually implements these. So my choice was kind of, well, do I use Haskell? I initially wanted to do that, but the problem with Haskell is that I wanted to move away from text. To do anything interactive or graphical in Haskell requires use of a knowledge of monads. And that's something that I didn't want to put on the user of the system. So another option was to build my own language, but I'm too lazy, and Michael already did that, so there'd be no point in that. So what I went for instead is this language called Elm. And Elm is very similar to Haskell from the programming style. If you can read Haskell programs, then you can definitely read Elm programs. But it has some key differences, one of which is that it compiles to JavaScript, so it runs inside the browser. What that enables is it can render graphics like it can render text. So it can give us a way of rendering graphics, a graphics library which is actually pure. It doesn't depend on any other input. And also, it doesn't have monads. Instead, how it exposes effects to the programmer is with signals. And signals are just an abstraction for time-varying values. And they're really quite interesting because if you wrap, so a signal is kind of a collection. It's kind of like a list. But a single value that's a signal refers to all possible values of a time-varying value. So if I ask for the mouse position in Elm, as you can see, it's a signal. These are all possible mouse positions ever, right? Not a single mouse position. Other libraries or whatever might give you just the latest mouse position. These are all mouse positions. So how do we get the actual values out of this? Well, we use higher order functions, right? So this whole thing is one signal. These things are values of that signal, and we can map them to a different type. We can select some of them, and we can fold over the past. This P stands for past. It's folding over the past. And interestingly, fold P is the only way in an Elm program to introduce any state in an application, which might seem pretty limiting, but when you think about what Elm is for for these sort of interactive graphical applications, any interactive application is really a fairly simple state machine over the user's input. And this actually constrains the programmer quite nicely. The more I've gotten to use it, I've really gotten to like it. So I think these are some pretty unique features. And what I'd like to show you now is what implications this has for the design of an editing environment that takes advantage of all of these features. So what I'm going to show you now, this is what an Elm file normally looks like, right? This is what you normally see. And normally a programmer interacts with this on, let's say, GitHub, right? This is the same file. So my editing environment, it's called Arrowsmith. It takes this code and then shows it to you like this. So the first thing you should note is that every single definition has its own text editor, its own editing field here. Definitions are the unit of code in a functional program. You should be able to reason about each of them separately, and you should be able to edit each of them separately. What giving separate text fields allows us to do is we can add further information about each definition. So for example, we can add its type, right? This isn't specified in the actual file. I'm parsing all of this from Elm's abstract syntax tree. What we can also do is we can add this little play button, which just evaluates a value. And it just shows it to me right there. I can obviously change anything, and it updates immediately, right? So that's not very interesting on its own because we can use a REPL for that. Where it gets more interesting is when we use values that don't have an obvious textual representation. So this, for example, can anyone tell me what this color is? It's red, right? Okay. Yeah, but because we're in a graphical environment, we can just show this. And this is actually an example of what I've implemented is a system for defining custom views that are type specific. So this is a specific view that's just for colors, which just shows a very simple rectangle with the color in it. So here's some other graphical types. So a form is just like any shape that's somehow filled in. And this depends on some color. I can obviously just change it around, and it changes color. But that's pretty ugly, so I'm not going to do that. So here I have some more functions that do some more stuff. So you have like this clock, for example. I can, of course, define new values. Right, and this just gets rendered. Nothing very exciting so far. I can like change this around, and the thing changes. Not super exciting, but where this gets interesting now is when we introduce time. So as you can see, I have this value now, which is of type signal float, which means that it's a float that changes over time, a floating point number that changes over time, provided by this library function every, which takes an interval. So another type-specific custom view that I have here is this view, which just plots a value over time. And as you can see, time just keeps on going up, right? This shows me that this is the Unix timestamp in milliseconds, and it just keeps on going up. But the interesting thing now is that I can map over this. Right, so first of all, let's look at the type of map, right? It takes a function and a signal, and then gives me back a signal of that other type.
Can you view map?
Can I view map?
Yeah, you said you should be able to view things that are not.
Oh no, so this
okay, so
no, I can't view at the moment, and that's something I'll actually get back.
You didn't provide a view for it. So
yes, I didn't. So currently, a limitation of these views is that they're not interactive. A really useful thing here would be you could just be able to like drop in values, but that's currently not provided.
I wasn't sure what map would look like anyway.
Well, it looks like this. What else do you need? Like,
So you're saying at some point we do think in symbols.
Again, I have some more prototypes which make these nicer, which didn't get implemented. I will show them after this demonstration because I think they're quite interesting. So what we can do, as you can see, I just applied all these values to it, and the type changed to a float, and this obviously just prints a sine wave over time.
So why do you have to divide it by 1,000?
Because it's in milliseconds, otherwise it would, like, it would go pretty crazy, like.
Yeah,
So that looks really cool, right? But there's something I don't quite understand about it, which is that if you just said wave equals 4.0, what would you see? Would you get a dot? Like, what's it? Okay.
Oh, oops, yeah.
Okay, you see.
Um,
What is it that made it know to draw a graph there?
it's the type.
So the type float means a graph.
No, the type signal float means graph. Because, oh well, actually, this is actually a bug here, but this just shows what would show if this wasn't, if we weren't using this view.
Right.
It would just show the latest value. But the interesting part here isn't that we can, well, another really interesting part is that we can also now do time-dependent graphics, which we can do like this. Now clock is equal to signal map clock over now, right, which is a signal of elements, and that just shows us the clock as it moves through time. So let's just enhance that. We'll make this tick so that ticks. We can add some more hands, one for the hour, for the minutes, and then one for the hour, and right, that just updates immediately. Okay. So what I want you to take from this are the following key points. Definitions are the unit of code. You should be able to edit each of them individually. You should be able to see information about each of them individually. You should be able to evaluate each of them individually. And you should be able to visualize them individually using context-specific graphical views to really show the true meaning of values. You know, if you just had that sort of number going crazy, you wouldn't really see the context over time. And what I want to provide here is a way to really add truly context-specific views that might just be for a specific data type that's only used in some project. Programmers should be able to do that. And of course, you should instantly see changes. The feedback loop between making a change and seeing it should be instant. And that's something that this does quite well already, but that you could do even better, really. So, well, what do we take out of this as a whole? I mean, the way we do programming hasn't really changed in the last few decades, but it really should. You know, we're kind of at a breaking point. Our computers...
You haven't worked at a 23-line terminal writing.
Sure, yeah, absolutely. Okay, by a few decades, let's say 2 decades, which is...
Even then, floppy disks, overlays.
I used that. I had floppy disks.
10 years.
Okay,
10 years. Okay, my experience spans to, let's say, whatever, 10, 12 years. I haven't seen it change as much as I expected it to change. And really, our computers are so powerful now that we're no longer within 80 by 24 terminals. Yet we're pretending as if we are. And really, we need to move forward. And the direction that we need to move forward in is really given by this principle that creators need to have an immediate connection to what they create. That's a really useful way to judge, well, are we doing the right thing? Another really useful way to judge whether we're doing the right thing is the conceptual framework provided by Brett Richter in Learnable Programming, which is totally ignored a lot of the times, that the design of a programming environment needs to be shaped by its underlying programming language. If the underlying programming language is weak, we can't build good programming environments. I mean, we can, we have, and, you know, they kind of work. It's just that if we sort of start from a lower level, we can make much more powerful programming environments. And, well, obviously there's some future work. How does this scale to, you know, like tens of thousands, hundreds of thousands of lines of code? That's really an unsolved problem at the moment. I believe that it can be tackled, but yeah, it's still something that needs to be done. And really, I'm talking about new ways of interacting with programs and whatever, but I haven't really looked at, you know, phones and tablets and touchscreen devices. What does editing code look like on those? And that's something that no one has really quite solved. And also, new methods of editing, what would those look like? Something that's not just typing text in an editor. And I thought I was going to run out of time, but I'm just going to show you these prototypes that I didn't manage to put in the system. But basically, I want to be able to visualize types even more, and really actually make them an integral part of the editing environment. Because, you know, in a functional programming language, types direct everything. You know, they really tell you what you can do with anything. So you should be able to drag, let's say, a list of floats onto a function that goes from a float to an element. You should be able to just drag it, and it should just do the obvious thing. It should just map it, right? That's something that, and I have a lot more in my report if you want to see those. And, well, let's just go back to why I did this thing in the first place, you know? I want computers to be tools for thinking, tools for creating, and tools for learning. And it's really only by playing around with stuff that you really figure out how something works, you know? This is refraction between like air and water. And you can see that after some angle, it actually just reflects it, right? And that's how optical fibers work, you know? That's something that's so obvious, but, you know, that's really difficult to get into your head if you don't see what's happening. So that's me. Thank you.